This is Q4. In Q4, we are asked to find the response of a sinusoid through an LTI system. So this is the diagram that we are interested in. This is the sinusoid. We call him x of n. And this is the LTI system, and we are supposed to find y of n. In this question, we have 4a and 4b. Let us do 4a first. In 4a, the LTI system h of n is described by this sequence 1, 2 followed by all zeros. So basically here is n equals to 0, and basically the response is 1, 2 followed by all 0 for h of n. So this is a finite sequence. Therefore, remember, when we want to find y of n, we can do it in many ways. Alright, the way that we are going to do is that we are going to try to find h of omega. So we take h of n to calculate h of omega. And in this case, this is very simple, because even though the Fourier transform, the discrete time Fourier transform of h of n looks like this, but because the sequence is finite, this equation is very easily gotten, and we can find h of omega. Okay, so in method 1, we use h of omega, the frequency response, to scale the eigenfunction. We call the sinusoid an eigenfunction because, remember, in our lecture we say that when a sinusoid passes through an LTI system, out comes the same sinusoid scaled by the original. So this is a magnitude scaling 2. We'll have the cosine. We'll have the same pi over 20n. We'll have the same phase shift plus pi over 3, but we have a new phase shift that is determined by the frequency response at this frequency. Omega in this example is equals to pi over 20, because that's the frequency of the cosine. Alright, there are other method 2, 3, 4, and we'll see the differences between them. Let's begin with method 1. Okay, our question is h of n equals to 1, 2, okay, so my question is different, 1, 2, and minus 3. I will update the tutorial for you later on. So our question is 1, 2, and minus 3. So I should draw here 1, 2, and minus 3. Alright. Anyway, because the sequence is finite length, we can very easily write this equation. N equals to 0 to 2. H of n e minus j omega n equals to h of omega. So we write this equation. We start with h omega equals to 0. We sum it for 3. The length is 1, 2, and 3, and the reason is because MATLAB uses length 1, 2, and 3. And we have this index h of n or h of k here, and then you must remember that this index over here must start from 0. So MATLAB will give you this issue because MATLAB's indexes for arrays starts at 1, while most of the time when we write equations, the index starts from 0. Anyway, once we have done this, we have executed this equation, and we are nice again, and we get h of omega as a complex number. So the other key idea is, what is w? Alright, what is w? Here, w in this particular example is equals to pi over 20. Okay, so this is the omega that we are interested in. And we are basically generating h of omega for only one particular frequency. Okay? We are not plotting for all of the frequency. We're only calculating the frequency response at this frequency because that's all we need. So we can then get the magnitude gain by using the absolute on h of omega, by the phase using angle on h of omega. And then the steady state response, which is y of n, is equals to the magnitude gain times the original A, and I remember it is 2 in our example, cosine, the small omega is pi over what? Pi over 20, and plus the phase shift in our example was pi over 3, plus the angle of h of omega equals to pi over 20. And that's it. This is the steady state response in this equation over here. And then now, so this is the magnitude gain. This is the phase shift. This is the original A. This is the original omega. This is the original phase shift. And now we can plot y of s. Alright, I mean you can study the working over here, but now we plot. Alright, now input x is 2, so it's the cosine with a phase shift. So that's the green guy. The red guy, y steady state, is, you can see all this, this is the y. And the only difference here is that the y is okay in the first two samples. Later on you'll see that using other methods, the first two samples is wrong, but the rest of the samples are correct. Okay, so therefore you'll see that the y at the steady state, it has become a smaller version of the cosine and a phase shifted version. So what is the gain? The gain is 0.626, meaning that 0.626 times 2 is about 1.25. So let's check. Yep, it's about 1.25 gain. And it has some phase shift. So we have just calculated method 1 in red. And 1 in red is called the steady state. Now let's zoom in into this part. Remember in this part, the time is time 0 and time 1. So it looks like it is the true response, but actually it's called a steady state response, basically because we're saying that if there was an infinite cosine, the green guy, sending into the system, then the output at time 0 and 1 would be like this. That means the input in the green guy must go into negative time infinitely, and this is the steady state response. If calculated by other methods, method 2, 3, 4, we'll have this. It's called the transient response in the input. Right, so I will continue this in the next video, but we have just done question Q4a method 1. Thank you.